If it's equidistant, if we want this to be equidistant from each point, so notice that this forms a triangle here. So when we had a triangle, how do we find something that's equidistant from each point? That was the circumcenter. That's the only one we've really talked about so far. So circumcenter. So if I inscribed a circle or circumscribed a circle around this triangle, the center of that circle would be equidistant from each of the vertices. And that's the circumcenter. To find the circumcenter, we do perpendicular. So perpendicular bisectors from at least two of the points. So wherever those perpendicular bisectors meet, so let's say like right here and right here, let's say those are the bisectors, that would be my point that is equidistant from each one. And the third one would meet two, but we only need to do two. So moving on to the next page, we have a theorem. So the next vocabulary word that we're going to be talking about is incenter. So the incenter does not use perpendicular bisectors, it uses angle bisectors. So that was the other thing we talked about yesterday, in yesterday's lesson 4.2. So the angle bisectors of a triangle intersect at a point that is equidistant from the sides. So this time, this point right here is the incenter. The incenter is equidistant from the sides of the triangle, not from the vertices. As you can see, going from point C to point P is a lot longer than going from B to P. So PD, PE, and PF are all the same length, as I marked on there. So in example 4, we got to solve for LK, given that point L is the incenter. So this is the incenter right here. LK is that length right there. We need to find that length. But remember, when we're talking about the incenter is equidistant from each side of the triangle. So that means that all three of these red lines that I'm drawing are all going to be the same length, because those are all the perpendicular lines to the sides of the triangle. So those are all the same length. So that means if I find LI or LG, that'll be the same length as LK. So if I could find either one of those, just like finding LK. Notice that if you look right here, let's see, if I look at this triangle, I'm just going to redraw it over here. So I have a right triangle. This is the side I don't know, that's LI. This side is 12. This side is 15. So I got a right triangle. I know two of the sides. To find the third one, I can use the Pythagorean theorem. So a squared plus b squared equals c squared. So 15 has to go where c is, and then it doesn't matter where 12 goes. So a squared plus 12 squared equals 15 squared. So a squared plus 144 equals 225. So a squared is going to equal, if I subtract 144 on both sides, a squared would equal 81. Take the square root on both sides, so a is going to equal 9. So that means LK is equal to 9. Then example 5, it says, suppose in example 4, you're not given HL or HI, but you're given that JL is 25 and JI is 20. So we're still trying to find, this time we're trying to find GL. Let's use the color here. So GL, LI, and LK are all the same length because this is the incenter, and the incenter is equidistant from each side. So each of these perpendicular lines from the sides are equidistant from this point. So I know if I find any of those orange lines, even though this one's going back to green, then I will find GL. Those are all the same as GL. So notice right here that we have a right triangle that we know two of the lengths of. So if I redraw that, So this is also a 90-degree angle. I know that this length is 20, this length is 25, and this is the length I don't know. So again, I could use the Pythagorean theorem. So a squared plus 20 squared equals 25 squared. So that'd be a squared plus 400 equals 625. So a squared is going to equal 225 and take the square root of both sides, and we get a is equal to 15.